My name is Pietro Martelli, and I'm a research associate at the Midea Materials Institute in Madrid. And today I'm gonna present to you our results in terms of ice cycle fatigue properties of a low carbon steel process using wire arc additive manufacturing. So additive manufacturing is currently spreadly used in many sectors, but in particular nowadays is gaining a lot of attraction also in the construction sector for the manufacturing of complex lightweight steel structures. And in particular, the main advantages in this sense are related to additive manufacturing techniques are the production flexibility, the freedom of design, the hybrid manufacturing, and the possibility of on-site printing and repairing. In particular, the results that I'm going to speak about comes from the Constructat project, which is a European project which aimed to develop a steel grade to be processed with different additive manufacturing technologies, in particular laser-based powder bed fusion, laser-directed energy deposition, both with powder and wire feedstock, and wire arc additive manufacturing towards the possibility of hybrid manufacturing. And in particular, today, I'm going to show to you our results from the one process. So very quickly, in this slide, you can see the setup and the process parameter for the technology. I won't read all the numbers. So I want just to acknowledge the Department of Mechanical Engineering of Polytechnic of Milan for the optimization of the process and the performance of the depositions. Regarding the steel, in the first phases of the project, different steel grades have been analyzed and studied, and finally we came up with the composition that you see in the slide. So we are talking about a very low carbon steel with a weight percentage of carbon less than 0.1% and low alloyed with silicon, chromium, molybdenum, manganese, and nickel. And in particular, the wire feedstock for the process has been provided by Bowler. It is a 3D print AM70 feedstock with a diameter of 1.2 millimeter. For the mechanical test, we performed two different depositions and we extracted tensile and fatigue specimens with different orientations, as you can see in the slide. So also to be able to assess possible anisotropy, which is typical for additive manufacturing technologies. Let's start with a quick overview on the microstructure. So the S-bit microstructure is basically tempered granular bainite, and this is the microstructure that we observed all along the deposited wall. And under the light optical microscope, we observed prior austenitic grains elongated towards the surface and along the building direction, so following the cooling heat flow. So from the EBSD analysis, we assessed just a slight texture between the 101 and 111 directions. We assessed the benetic packet size at less than 1 micrometer of equivalent diameter as average value. And we also assessed the kernel average misorientation distribution. And we saw that actually we have a uniform distribution of the KAM values with no retained austenite from the process. So now let's move to the mechanical test. We performed tensile and ice cycle fatigue test, in particular tensile test in strain control at 0.2 millimeter per minute, while the fatigue test in pull-pull condition with a stress ratio of 0.1, setting the runout at 10S7 cycles and testing with a frequency of 50 Hertz. So let's go to the result from the mechanical test. Surprisingly, we did not assess any anisotropy from the material, because if you look at the value and you consider the error bars, we can say that actually there is almost no anisotropy in the results. We obtain a yield strength between 430 and 470 megapascal and an ultimate tensile strength between 770 and 810 megapascal, while the elongation at fracture was assessed higher than 10 and 12, the uniform elongation higher than 10%, and the elongation at fracture higher than 12%. So very good results in terms of ductility for this material. And then from the fatigue test, we assessed in the first instance the fatigue limit. So plotting the delta sigma against the number of cycles to failure. So the fatigue limit at 7 cycles. Also in this case, if you look at the points, we see that they overlap basically. So there is almost no anisotropy also in the fatigue properties, because due to the limited number of test specimens and so limited statistics, we assess the fatigue limit at 540 and 531 megapascal of delta sigma for the different configuration. But again, it's also due to the limited number of available specimens. So if you look at the point, actually, we can say that the material behaves basically the same way between the two configurations. Now, this is a material property. Usually, it is typical to see fatigue properties in terms of fatigue limit at the runout. But since this material is thing to be used and developed for the construction sector, another thing that was important for us to assess was the fatigue strength at 2 by 10 at 5 cycles according to the Eurocode 1993-19. In this Eurocode, we have different categories assessing the fatigue properties of structures. And in particular, what you see plotted in the graph is the highest category for the Eurocode, which is the category 160 with the two different slope 3 and 5. And if we compare our points to this limit, to this reference curves given by the Eurocode, we see that the performance of our steel is incredibly high with respect to these reference values. And the same we saw in the literature. So I reported a reference work by Tong et al. That tested in the same conditions high strength steel series, so different high strength steels in the same condition, and the delta sigma E that we assessed at 2 by 10 at 5 cycles being 550 megapascal was in the range of 170 to 150 megapascal. Why this discrepancy? We linked this very different behavior to the microstructure, because usually steels in construction present a paralytic ferritic microstructure. And we now have from the additive manufacturing technology a very fine bainitic microstructure. So we think that, and also the Eurocode was based on traditional microstructure. So we think that this is the reason why the material properties significantly different, should present a significant difference also with respect to the Eurocode, which is, but these results says that this material is a promising steel for the construction sector. And finally, from the photography point of view, we observed superficial nucleation of the fatigue crack with transgranular propagation. And what we observed is that the condition for the fracture nucleation is basically independent from the orientation and the stress level. So also this is important with respect to the anisotropy of the material. So just to conclude, we processed our low carbon steel with one technology, and we obtain a very fine bainitic microstructure. We assessed no anisotropy in a static condition, both regarding the yield strength, the UTS, and also the ductility, which was very high, so above the 10% regarding the uniform elongation. We assessed through the fatigue test, the fatigue limit at 10 at 7 cycles being delta sigma of 540 and 531 megapascal for the 90 and 0 degree configuration. But since the material is intended to be used in the construction sector, we also assessed the fatigue strength at 2 by 10 at 5 cycles being delta sigma 550 megapascal, which is an outstanding result that we attributed to the very fine novel microstructure obtained by the wire arc additive manufacturing process. And finally, we observed fatigue crack nucleation was superficial with the transgranular propagation. So thank you for your attention.